All right, so in lecture 15 here, we're going to discuss connected sets. So a connected set is just, it's a set that's all in one piece. And it's one contiguous mass of stuff. And so what we're going to do to define a connected set is describe what it means for a set to not be connected. And then say a connected set is not that. So the idea is if you have, a disconnected set, so let's say your S is the union of A and B. So this is your, actually let me use a color. So A union B. So a set that's not connected, a disconnected set, is going to look something like this piece in red here and this piece in blue here. And the way we're going to be precise about the fact that this set is disconnected is the following. So what we're going to say is that this set is disconnected if we can put open sets in here so that this A half is insulated from the B half, and also that the B half is insulated from the A half. So what we can do here is, so let's say this is an open set over here. Right, so this open set U is going to contain the set A. So over here, so what we have here is that this U, so if we take U and intersect it with S, we get A over here. Okay, so there's got to be some open set which insulates A from B. And also there has to be some open set, let me use a color here, I guess. There's got to be some other open set, say V, over here, which insulates B from A. Okay, so this, so over here what we have is that if we take this set V and intersect with our set S, that gives us the B half of the set. Okay, so that's basically the idea of a set being disconnected or not connected, is that we can break the set into two pieces that are insulated from each other, in the sense that those two halves, they're each contained in some open set, which separates it from the other half. So let's write ourselves a definition here. So definition. A set S is disconnected if there are open sets U and V such that, so we just have to write down this picture here. So the two different halves of the set, we're going to have U intersected with S, that's going to be one thing, and U and V intersected with S, that's going to be the other thing. And those two have to sort of add up to be the whole set. Okay, so such that S equals S intersect U union S intersect V, and two additional things. So the two additional things are that these, right, so each of these two halves, so this is your A and this is your B, those are disjoint sets, so no overlap between them, and they're not disjoint for the trivial reason that one of these things is empty. Okay, so in other words, both of these halves have to be non-trivial, have to be non-empty. Okay, so we have that they're going to be disjoint. So S intersect U intersect S intersect V is equal to the empty set, but neither of those things are the empty set. S intersect U itself is not the empty set, and S intersect V is not itself the empty set. Okay, so what we have here is, so we have this disjointness. So let me want to pick a color here. Okay, yeah, so we'll just say, so this is disjoint. So we have the disjoint property. Maybe I'll use capital letters. So disjoint, and here we have non-empty. And then up here we have open. So there's sort of three things to remember in this definition for disconnected. So we're starting with open sets. Okay, so those open sets, they break our original set into two pieces. Okay, so each open set intersects with S, and that is supposed to give us two pieces. Okay, so we have these open sets slicing through our set and giving us two pieces. And our set's going to be disconnected if those open sets do this in such a way that the pieces are disjoint and they're non-empty. Okay, so my topology professor in grad school, Don Davis, shout out to Don Davis if he's out there listening to it, great man and mathematician. He told us to remember, so Don Davis told us to remember the acronym DON here for the situation for connected or disconnected sets. So when you're trying to remember this, this definition of disconnected, remember you're starting with these open sets, and then once you have these two halves, they have to be disjoint and non-empty. So that's open, disjoint, non-empty. Okay, so we have disjoint, open, and non-empty. All right, so that's the acronym to remember for the definition of disconnected. Okay, right, so this, another little definition. So these two sets here, the S intersect U and S intersect V, those are called a separation of the set S. So the sets A equals S intersect U, B equals S intersect V are a separation of S. And so we'll just make a separate definition just to canonize this concept. So a separation of a set S is a decomposition. It's a decomposition S equals A union B, such that there are open sets. So we're just sort of rewriting this stuff up here. So this will just sort of give us another way of discussing the same thing. So separation is a decomposition such that there are open sets UV with A equal to S intersect U and B equal to S intersect V. And additionally, A intersect B is equal to the empty set. And we're just rewriting we're just sort of rewriting this with a primacy. The primacy here is on the sets A and B instead of on sort of the open sets U and V up here. And so it's really in a way just kind of rewriting part of that definition up there. So we have this intersection equal to the empty set, but A is not the empty set and B is not the empty set. Okay, so another way to say, so in other words, S is disconnected if there's a separation of S. So my professor, Professor Don Davis, called these sets A and B Don sets after himself, humbly enough. So the A and B, the O in Don is for open, right? So these A and B, they come from intersecting the set with open sets. They are disjoint, that's the D, that's this first condition here, and they are non-empty. Okay, so they're not the empty set. So I know there's a number of components here. It does, this definition does come from this kind of simple picture up here, but it can be kind of a little bit annoying to remember all of the conditions. So having that acronym is helpful. All right, so the first thing substantive they have to talk about after the definition is the fact that this is not the definition that's given in the book for a disconnected set or for a separation of sets. This is the way I learned the material, and it's the way I still think about the material, so I don't know. I think I find this a more intuitive way of thinking about the concept of disconnected, but I would like to make the connection with the way the book discusses the situation. And so that's what I want to turn to now, showing that the way I'm talking about this here is equivalent to the book's way of going about it. And maybe that'll just help clarify the situation generally. So here's how that's done. So one consequence of this picture here, so if we're looking at a separation of a set S, the fact that you have this open set U here, such that U intersect with S is equal to A, that tells you that this set B is contained in the complement of U, right? So U is this open set over here, and then we have the complement of U over here is this closed set containing B. So in particular, we have this closed set containing the set B, then the complement of U must contain the closure of B, right? Because the closure is the smallest closed set which contains B. So we'll have the closure of B being contained in the complement of U. So in particular, the set A is disjoint from the closure of B. And then reversing the roles of A and B, we see also that the closure of A has to be disjoint from B because A is contained in V complement. So we have this big closed set containing A, and therefore the closure of A is contained in that closed set. And so that's another way of thinking about this idea of disconnected, a separation being a way of insulating two halves of a set from each other. So this open set barrier here that we've set up between A and B, another way of saying that is that the closure of A doesn't meet B. So it's not just that A and B are disjoint, it's that A is actually disjoint from the closure of B. So it's disjoint from any limit points of B, and vice versa similarly. So B is disjoint from the closure of any for any limit points of A, from the closure of A. Okay, so that is the equivalent definition that the book uses for a separation, and we'll state that as a theorem here, or as a proposition. So here's our proposition. The sets A and B are a separation of S if and only if S equals A union B, A and B are not empty, and so this is stronger than, so this condition here is stronger than disjointness. And so not only are A and B disjoint, but actually A is disjoint from the closure of B, and B is, oh, sorry, I just rewrote the same thing twice. So this should be A closure intersect B. Right, so A is disjoint from the closure of B, and the closure of A is disjoint from B. Okay, so this is stronger than saying that the sets are disjoint, and this is strong enough to imply that these sets A and B come from open sets, from taking open sets and intersecting them with S. Okay, so we still have the non-empty part, but we can replace the D and the O, the disjoint and the open part in Don with this single condition here. Okay, so let's take a look at the proof. So suppose A and B are a separation of S. So that S equals A union B. A is not the empty set, B is not the empty set, so they're non-empty. They're disjoint. A intersect B is equal to the empty set, and here's the open condition, and there are open U and V such that when I take S and I intersect with U, I get A, and when I take S and intersect with V, I get B. Okay, so then the only condition we have to verify is this last one. So we just need to, verify that A intersect B closure is empty and A closure intersect B is empty. So it's just the argument we gave above, but just sort of quickly and with the picture. So if you have your A and your B, the picture is that you're going to have the set U here, right? So U is over on this side, and then you have V. V is over here. And what we want to say is that B is contained in the complement of U, right? So U is this open set surrounding A, so its complement is this closed set surrounding B. So what we'll say is, so notice that U, so if I take U and I intersect it with B, well, because B is in the set S, I can just do a little trick here. This is the same thing as U intersect S intersect B. And that's just A intersect B. Okay, so really, if you just expand this A intersect B in terms of just substitute A equals S intersect U and B equals S intersect V, you can delete one of the S's, and you see that U intersect B is equal to the empty set. And then similarly, we can do a similar computation with V intersect A. So V intersect A, I can write that as V intersect S intersect A. That's B intersect A. And that is the empty set. So what that tells us, so thus B must be contained in U complement, and A must be contained in V complement. So since U complement and V complement are closed, in fact, B closure is contained in U complement, and A closure is contained in V complement. And this is equivalent to, so which is equivalent to so if this set is contained in the complement of U, that just means that U is totally disjoint from B closure. So we can write this as B closure intersect U equals the empty set, and A closure intersect V is equal to the empty set. And remember, what we want to conclude is that actually the closure of, say, B is disjoint from the set A, but A lies inside of U, right? By definition, A is a subset of U. So what we find, but then A intersect B closure, that is contained in U intersect B closure, which is equal to the empty set, and A closure intersect V is contained in A closure, or sorry, wrong way around. A closure intersect B is contained in A closure intersect V, and that's equal to the empty set. So A intersect B closure equals the empty set, and A closure intersect B is the empty set. And so that that shows that the condition, the required condition, holds. Okay, so that's the proof in one direction. So now we'll suppose, that S equals A union B, that these sets are non-empty, and that we have that condition which is supposed to replace the disjoint and the open. So we have that is equal to the empty set, and A intersect B closure equals the empty set as well. Okay, so let's see. So what do we have to show? So we need to show, well, we have the fact that the sets are non-empty. So A and B are non-empty. And of course, this condition here is actually stronger than the fact that they're disjoint. Okay, so we automatically have that A and B are non-empty, and that A intersect B equals the empty set, since A intersect B is, it's a subset of either one of these two things here, which is the empty set. So all we need to show, so it remains to show that there are open sets open U and V such that when you take U and intersect it with S, you get A, and when you take S and intersect it with V, you get B. But it is now fairly obvious where these sets are coming from. So if this is your A here, and this is your B here, well, what we know is that not only are A and B disjoint, but actually the closures of these sets are disjoint from each other. So when you take the closure, the sets are still disjoint, right? So this is now A closure and B closure. And so, well, A closure is, well, sorry, actually I should say, sorry, if we take the closure of A, so just take the closure of one of them and then leave B what it is. Now, these two sets are disjoint, right? So, well, the closure of A is a closed set, so what I can do is look at the complement. And so this complement must actually contain B, right? So that's going to be, so the complement of A closure is going to be my open set, which when intersected with S gives me the set B. And then similarly, when we take B closure and just leave A as itself, B closure's complement is going to contain A. And so those are going to be our open sets. It's just going to be the complements of the closures of each of the sets. So what we do, or what we can do is, so it comes from these two facts here. So from A closure intersect B equals the empty set, and A intersect B closure equal the empty set, we deduce that, so from the first one, B is contained in A bar closure, and A is contained in B bar closure. And what we'll do is we'll set U to be equal to B bar closure and V to be equal to A bar closure. And then all we have to do is verify that S intersect U is A and S intersect V is B, and that should be actually a quite mechanical set theory computation. So then S intersect U, that's S intersect B bar closure, but S itself is A union B. So we have A union B intersect B bar closure. But one thing I think we did on the first homework assignment is show that this, you can just distribute this over the intersection, or over the union, right? The intersection distributes over the union. So you get B intersect B bar closure, or sorry, B closure complement. And of course, B closure is a set that's bigger than B, so its complement is not going to intersect with B, right? So this is actually going to be the empty set. So this equals A intersect B bar closure, and then union the empty set. And this set here, well, remember, we have the B bar closure is contained in A, right? So B bar closure here, so this A intersects B bar closure, that contains A intersect A. In other words, it contains A, but also obviously, right, as an intersection, this is contained in A. So it must just be A. So this is just A. So this is, since A is contained in B bar closure, and since obviously A intersect B bar closure is contained in A. So we have that computation, and then an entirely analogous computation. S intersect V is going to be A union B intersect with A bar complement. That's just going to be A bar complement intersect B. We're just going to get the empty set from the other one. And again, this is just going to be equal to B, because this set must contain B intersect B from this fact here, but it's also contained in B. And that's so since B is contained in A bar complement, and A bar complement intersect B is contained in B. Okay. All right, and so actually that completes our proof then. Okay. So that is the last step of the proof. Okay, so this whole discussion, this just gives us two different ways of talking about the notion of a set being separated. So we either have the set is a union of two pieces, and the two pieces are so-called Don sets. So they're disjoint, they're non-empty, and they each come from intersecting S with an open set. Or we have this this condition here, which is that they're non-empty, and we have this kind of stronger disjointness condition here, which turns out to be sort of equivalent to the openness and the disjointness. So this condition here replaces the D and the O in Don. Okay, so we still have the N, and then this is both of those conditions put together into one single condition. So this is kind of simpler to understand, but I think it's a little bit less intuitive. So I didn't want to make it the definition. I thought it was more intuitive to start with the other definition and then kind of work our way towards the book's definition. Okay, so the book uses this condition here as the notion of separation as a definition, and doesn't even talk about my definition. Okay, so kind of giving you a little bit of a more expanded perspective on this concept of a set being disconnected or a set being separated, having a separation. All right, anyway, so that's all disconnected sets. And so now we have sort of the main definition, which is just that a set is connected if it's, so a set is connected if it's not disconnected. If it's not disconnected, i.e., if there is no separation of S, if there is no separation of the set. All right, so it's definitely time for some examples. So let's look at some examples. So one thing is it's actually kind of hard to show that sets are connected. So I can give a couple of trivial examples of connected sets and then a couple interesting examples of disconnected sets. So it's easier to show disconnected. All you have to do is find a proper, decomposition into Don sets, or find a separation of the set. But to show connected, you have to show that you can't do that in any possible way. So that's a little bit more subtle and involved. So first example of a connected set is that, so if we have any one-point set in Rn, this is connected. And that's fairly simple, so I guess we'll call this S. So if S is equal to A union B, then the only possibilities are A equals A and B equal to X, or the empty set, and not both the empty set. But the problem with that, of course, is that to be a separation, right, that neither of them can be the empty set. But then if neither of them are the empty set, then the only option is that they're both this set containing with a single point X in it. But then they're the same set, right? Then they're not disjoint. So we can say is that, but then A intersect B equal to the empty set forces A or B to be the empty set. So A and B are not both non-empty. Okay, so a one-point set is always connected. Another example is even more trivial, is the empty set is a connected set. So S equal the empty set itself is connected. And that's just because if A union B equals S, then A and B are both the empty set. So A and B cannot be non-empty. And so there's no separation. No separation of S. Okay, so those are the only two examples that are really easily accessible without some argumentation. So we will see by the end of the lecture that R itself is connected, and actually that any interval contained in R is connected. So that will give us a decent place to start with connected sets, and sort of confirms our intuition that those sets should be, of course, considered connected. So let's give some examples of disconnected sets. So if S equals U union V, or well, actually, let me say, let me say A and B to not be confusing. So if A equals A union B, where A and B are disjoint, and A and B are open, then S is disconnected. Okay, so any union of disjoint open sets is a disconnected set. I suppose, sorry, I keep forgetting I have to be very pedantic about this. A and B are non-empty open sets. So I'm going to say non-empty and open, then S is disconnected. And so this is sort of obvious. We have the disjoint just by our hypothesis. They're non-empty, and then the open condition just comes from the fact that, well, A is just A intersect S, right? And A itself is open. And B is just B intersect S, and B is open, right? So here you can take, to see this, just take U equal to A and V equal to B. Then A, B are obviously a separation. Okay, so, specific examples of this, you can imagine, you can take intervals in R like far apart, like, 0, 1, and say 2, 5, but even intervals, open intervals that seem to kind of almost touch each other are going to be separated. So a specific example, is the set S equal, say, take 0, 1, and then the union of that with 1, 2. Okay, so even though these, you kind of, when you draw this picture, these seem, so you have, your intervals, the set looks like this, right? So there's like no negligible space here in between. But nonetheless, this is considered not connected. And sort of intuitively, right, to sort of travel through this set, you have to pass through this point, which is outside S. So in an intuitive sense, you would say this is not connected. You have to travel outside the set to make it to the other half here. And yeah, you can see it from the other description too, because the closure of this of the set 0, 1, that's just the closed interval, and that's disjoint from 1, 2. And the closure of 1, 2, that's just the closed interval, that's disjoint from this open interval. Okay, so even open sets that are practically touching are still considered to be disconnected. Okay, so you can imagine open balls that kind of just barely are sort of kissing at a point. Those would sort of be the analog of this situation in higher dimensions. That would also be considered disconnected set. A very interesting example of a disconnected set is the rationals. So S equals Q is disconnected. So here we can just take A to be Q intersect with the interval from negative infinity to the square root of 2, and B to be the rationals intersect with the interval from square root of 2 to infinity. Okay, so we obviously, then S equals A union B, clearly. Also, A intersect B is empty, clearly. Okay, so so we have the union here. They are disjoint. They're non-empty. A is not equal to the empty set, and B is not equal to the empty set. And these sets come from an open set, right? So we have this open set intersecting with our set S to make the A and B. And A and B come from open sets. So that that substantiates the claim. Okay, so that gives us hopefully a decent number of examples to chew on and reinforce the intuition. So now, returning to the definition, it might bother some that connected is phrased in terms of a negation of another condition, that there's not a sort of positive statement for the definition of connected. But we can extract a positive statement from what we've done here. So what we can do is come up here. So a set is connected if it's not disconnected. And a set being disconnected means this, right? That we can write S as this union of things that are non-empty and such that this condition holds. So what we can say for S being connected, so a set is connected if anytime you write S as a union of non-empty sets and let's say that the sets are disconnected. So every time you break S into two pieces which are non-empty, you have the failure of this condition. Okay, so because we're talking about connected, which is the negation of this condition. And so if we have these things holding, then this thing must fail here. So in other words, it either has to be the case that limit points of A are falling into B, or limit points of B are falling into A. Okay, so we get a little proposition that characterizes connected in a more positive fashion. So here's a proposition. So a set S is connected if and only if whenever we write S equals A union B for disjoint non-empty sets A and B, then there are either limit points of A which get into B. So A closure. So it has to be the case that either A closure, remember the condition, A closure intersect B equals empty set, and A intersect B closure equals empty set. So it has to be that one of these is going to fail. And since we're taking our sets A and B to be disjoint, what it must be is that the limit points that we've added in must be falling into B to make this not equal to the empty set, or the limit points of B must be falling into A to make this not equal to the empty set. So I'll say then either there are limit points of A in B or limit points of B. Sorry, I don't know. I said limits instead of limit points. Sorry. Then either there are limit points of A in B or limit points of B in A. Okay, so that's an equivalent characterization of connected. And it's just as straightforward using the proposition that we already have and just negating the definition of connected. So the proof is just exercise, a simple exercise. So this is simple exercise, basically just shuffling around, shuffling definitions and propositions we've already covered. Okay, so we'll just leave it at that. So the final topic is just going to be to actually produce some non-trivial examples of connected sets. So here we'll have a section R and intervals are connected. All right, so the proposition here, or maybe we'll call this one a theorem. So the theorem is that a subset S of the reals is connected if and only if it has this property which the real numbers and any interval in the real numbers have. So it's connected if and only if whenever A and B are in S, and C is between A and B, then C is in S. Okay, so sort of intuitively, if any two things are in S, then the whole interval between A and B is in S. Okay, so if a subset has that property, then it's connected, and vice versa. If it's connected, it has that property. Okay, and of course, any interval has this property. So this proposition will immediately imply that intervals, and in particular R, are connected subsets. And intervals covers any kind of interval, a finite open interval, a potentially infinite. One right endpoint is an infinity, or the left endpoint could be a negative infinity. The intervals could be half open or open, right? All those types of intervals satisfy this property. So that's why it's kind of easier to use this property and prove this proposition than to talk about intervals, because there's so many different kind of types of intervals. It's just easier to use this property here. Okay, so let's then look at the proof. So suppose we'll go forward direction first. So suppose S is connected and A and B are in S. If C satisfying A less than C less than B is not an S, then what we can do is set A equal to negative infinity up to C intersect S, and B equal to, sorry, I'm going to run out of room there, and B equal to C to infinity intersect S are a separation of S. Okay, this is clear because this capital A set has little a in it. This capital B set has little b in it, so they're non-empty. They're clearly disjoint. They come from open sets, and so therefore they constitute a separation of S. So since S is connected, this can't happen. And so C in S follows. Okay, easy peasy that way. More substantial and somewhat less intuitive argument is the other direction. So we have to actually take this kind of subset with this property and show that it has the connected property. So we have to show that whenever we have a whenever we write S as a union of disjoint sets that are non-empty, then a limit point of one of those sets bleeds into the other set. So let's write S as A intersect, no, sorry, not intersect, A union B, where A and B are not empty, and A intersect B is the empty set. Okay, so these are disjoint. And so what we want to show is there's a limit point, a limit point of one of these sets, a limit point of one of A, B is in the other set. So since A and B are non-empty, there is an A in A, and little b in B. And without loss of generality, just by reversing the names of A and B, and without loss of generality, we can assume that A is less than B. Okay, of course, so these sets are disjoint, so A can't be equal to B. One of them is less than the other one, and so we might as well just assume that it's A, that it's less than B. So by our assumption, the interval from A to B is contained in S. And what we're going to do is just focus on this interval. So we'll take this decomposition of S into A union B, and we'll just look at it in the interval from little a to little b. So write the interval AB as, so take A, so we'll look at everything that's in AB that's in the big set, big A, and we'll look at everything in the interval which is in B. And of course, since A and B exhaust this set S and our interval is contained in S, this is a decomposition. This equality does hold. And we'll call this, so this first set, we'll just call it A naught, and let's call the second set B naught. Okay, so it's easy to see since the point little a is in A, this A naught is not empty, right? So we have A in this little a in this interval, little a in A, so this is not empty. Similar with B over here, so this is non-empty. And if these two sets were to intersect, then that would mean that A and B intersect, right? So these sets are also disjoint. So observe that A naught is not equal to the empty set, and B naught is also not the empty set, and the intersection of these two things is the empty set. Okay, so we're focusing all of our attention on this interval here, and we have it split into two pieces. And so what we're going to do is we're going to find a limit point of A naught or B naught, which is in the other one. Okay, and since a limit point of A naught is going to be a limit point of A, and B naught is contained in B, that would do the job, and vice versa with the roles reversed. And so it suffices to just find a limit point of one of these A naught, B naught sets and observe that it's in the other set. So we will show that a limit point of one of A naught and B naught is in the other set. So what we'll do to produce this limit point is we'll just look at the supremum of A naught. Okay, so clearly, A naught is a non-empty set, and it's contained in this bounded interval here from A to B, and so we have a supremum. So indeed, let S equal the supremum of A naught. So since B bounds A naught above, we have that S is less than or equal to B. And so S is, of course, in this interval from A to B. So thus, S is in one or the other of these two sets. So S is in A naught or S is in B naught. And we'll show that in either one of these cases we get the desired conclusion. So on the one hand, if S is in A naught, then since little b is in B naught, we have S less than B. Right, so S can't be B, so it must be less than B. Well, this means that the entire interval, so the interval from S, not including S because S is in A naught, but from S up to B is non-empty, and a subset of B naught. Right? There can't be anything from A naught in here because S is the supremum of A naught. But then for any ball, right, any small ball, right, any ball of any size around S must intersect this interval. But then there are points of B naught in any small interval, so any interval S minus epsilon, S plus epsilon for epsilon greater than 0. So that tells us that, so S is a limit point. Right, so remember, what does it mean to be a limit point? Well, actually it's, there are points, so there are points of B naught, which of course S is not in B naught, right? So there's points of B naught in the punctured interval, so in this interval, but not equal to S. So that tells us that S is a limit point. So S is a limit point of B naught. Thus, in this case, A naught, a limit point of B naught. So we have A naught intersect B naught bar. That's contained in, is not the empty set, right? So this is not equal to the empty set. Which implies that A intersect B naught is not the empty set, right? Because this set contains this one. On the other hand, if S is in B naught, what does that tell us? Well, if S is in B naught, I mean, S is the supremum of A naught, but the supremum is always a limit point of the set that it's the supremum of. S is in B naught, we merely use the fact that since S equals the sup of A naught, it follows that S is a limit point So maybe just to elaborate on that, so there must be points of A naught in, so if we take S minus epsilon up to S, right, so there must be points of A naught in that interval, but S is not in A naught, right? So there are points of A naught in S minus epsilon, S plus epsilon star, or say that minus the point S. Right, so to be a limit point, you have to be in the punctured ball around that point. So I'm just being, necessarily pedantic about that. Okay, so in this case, we have that A naught bar intersect B naught is not the empty set, so A bar intersect B is not the empty set. And this completes the proof. Okay. So yeah, that was a bit of a, that one's a non-trivial one. Proving anything is connected is not so easy from first principles. But in any case, we get the happy corollary that R is connected, so R and any interval in R are connected. And just the proof is that these sets have the property in the theorem. Okay, so they have that property which is proven to be equivalent to connectedness in the theorem. All right, so I think that's everything I'm going to say about connected sets. And so I will see you again after spring break for more.